the sampling distribution of the sample mean for a normally distributed variable. Suppose that a variable x of a population is normally distributed with a mean mu and standard deviation sigma. Then, for samples of size n, the variable x bar is also normally distributed and has mean mu and standard deviation sigma divided by the square root n. Central limit theorem. For a relatively large sample size, the variable x bar is approximately normally distributed regardless of the distribution of the variable under consideration. The approximation becomes better with increasing sample size. Sampling distribution of the sample mean. Suppose that a variable x of a population has mean mu and standard deviation sigma. Then for samples of size n, the mean of x bar equals the population mean, or the mean of the sample means, which equals the population mean. The standard deviation of x bar, the sample mean, equals the population standard deviation divided by the square root of the sample size, or standard deviation of the sample mean equals the population standard deviation divided by the square root of n, which is the sample size. If x is normally distributed, so is the sample mean, regardless of sample size, and if the sample size is large, the sample mean is approximately normally distributed regardless of the distribution of x. Example: according to one study, brain weights of men are normally distributed with a mean of 1.20 kilograms and a standard deviation of 0.15 kilograms. Determine the sampling distribution of the sample mean for samples of size 3. The two formulas that we want to use are the mean of the sample means equals the population mean, and the standard deviation of the sample means equals the population standard deviation divided by the square root of n. For this problem, our mean is 1.2, so the mean of the sample means is 1.2. My standard deviation is 0.15, my sample size is 3. Substituting, I have 0.15 divided by the square root of 3, which gives me 0.0866. The sample mean is 1.2 and the sample standard deviation is 0.0866. Continuing with our example, we have the same mean and standard deviation. In this example, determine the sampling distribution of the sample mean for sample sizes of 12. We are using the same formulas as the previous example, so our mean of the sample means is still 1.20. For the standard deviation of the sample means, we still want to use 1.5, but this time our n is 12, so we have 0.15 divided by the square root of 12, which gives us 0.0433. The sample mean is 1.2 and the sample standard deviation is 0.0433, both in kilograms. Continuing with our example, construct a graph of the normal population distribution and the two sampling distributions for brain weights. We start with our number line where our mean is marked 1.2 as the center. Our population curve is our normal curve with a standard deviation of 0.15. Our next curve is the mean of the sample means when n equals 3, the standard deviation of the sample means of 0.0866. Then we draw our last curve where I have a mean of 1.2 and my sample size 12. The standard deviation of the sample means is 0.0433. Continuing with our example, Determine the percentage of all samples of 3 men that have mean brain weights within 0.1 kilograms of the population mean brain weight of 1.20 kilograms. When we draw a sketch of the normal curve, the mean is in the middle and there are lines on each side to represent the interval. Shade between the lines to show the area under the curve. My mean is 1.20. If I were to subtract 0.1 kilograms, I would get 1.1, which is the data point to the left. If I were to add 0.1 kilograms, I would get 1.3, which is the data point to the right. Using my formula to find my z-score, z equals sample mean minus the population mean divided by the population standard deviation divided by the square root of n. Starting with the data point 1.1, we substitute z equals 1.1 minus 1.2 divided by 0.15 over the square root of 3. Going to our calculator, when we type this in, we need to make sure that we have parentheses around the top. Parenthesis 1.1 minus 1.2, close parenthesis, divided by, and then parentheses around the bottom. Parenthesis 0.15 divided by, second, x squared gives us our square root, 3. I'm going to arrow to the right and close my parentheses. Enter, and we get negative 1.1547. So I have a z-score of negative 1.15. Next, I want to use the data point of 1.3. Z equals 1.3 minus 1.2 divided by 0.15 divided by the square root of 3. Calculating. I'm going to press second and enter, which retypes the previous entry. Then I'm going to arrow to the left so I can change 1.1 to 1.3. Enter. And my z-score is 1.15. If you notice, we have a z-score of negative 1.15 and positive 1.15. Because our normal distribution is symmetric, a shortcut that we have is that once we find our first z-score, to find our second z-score, we just have to change the sign. Now I'm ready to find the area. I can either use my table or use my calculator. For this one, I'm going to use the calculator. Second, and my VARS button to get to the distribution menu, I want number 2, normal CDF. For the normal CDF, you need a lower limit and an upper limit. My lower limit is negative 1.15. My upper limit is positive 1.15. I'm going to leave my mean as 0, standard deviation is 1. Enter. If you did not have the stat wizard, when your normal CDF came up, you would just type negative 1.15, comma 1.15. 0 and 1 are the defaults. Enter, and I get 0.749856. Rounding to 4 decimal places, I get an area of 0.7499, which is 74.99%. According to one study, brain weights of men are normally distributed with a mean of 1.2 kilograms and a standard deviation of 0.15 kilograms. Determine the percentage of all samples of 12 men that have mean brain weights within 0.1 kilograms of the population mean brain weights of 1.20 kilograms. The only difference between this example and our previous example is that instead of n equaling 3, n will equal 12. The normal distribution sketch is the same as the previous example, with a mean of 1.20 and 1.1 to the left and 1.3 to the right. The area under the curve between 1.1 and 1.3 is shaded. I'm still using the z-score formula, the sample mean minus the population mean divided by the population standard deviation divided by the square root of n. When I substitute, I have z equals 1.1 minus 1.2 divided by 0.15 divided by the square root of 12. Going to my calculator, press second, enter, then second, enter again, then second, enter for a third time, so that I have my parentheses 1.1 minus 1.2, then divided by parentheses 0.15 divided by the square root of 3. Arrow over the 3, change that to 12. Arrow out, make sure I have a closed parenthesis, enter, and we get negative 2.309. And rounding, I have a z-score of negative 2.31. Substituting the 1.3, z equals 1.3 minus 1.2 divided by 0.15 divided by the square root of 12. Heading back to my calculator, press second, enter, then second, enter again, then second, enter for a third time, so that I have my parentheses 1.3 minus 1.2, then divided by parentheses 0.15 divided by the square root of 3. Arrow over the 3, change that to 12. Enter, and we get 2.309. And rounding, I have a z-score of 2.31. The shortcut way to find the second z-score, since our normal distribution is symmetric about the mean. Once you find z equals negative 2.31, I can change the sign to find my other z-score of a positive 2.31. Now I would like to find the area. Going back to my calculator, second, enter, second, enter, second, enter. My normal CDF comes back up. And then I'm going to arrow over and change my negative 1.15 to 2.31. And then my positive 1.15 to 2.31. Enter. And I get 0.97911. Using 4 decimal places, that rounds to 0.9792. Which is 97.92%. Example, find the probability and interpret in terms of the sampling error. An ethanol railroad tariff is a fee charged for shipments of ethanol on public railroads. An agricultural association publishes tariff rates for railroad car shipments of ethanol. Assuming that the standard deviation of such tariff rates is $1,000, determine the probability that the mean tariff rate of 350 randomly selected railroad car shipments of ethanol will be within $90 of the mean tariff rate of all railroad car shipments of ethanol. Let's start with the $1,000. That is our standard deviation. The 350. Since that's the randomly selected cars, that's our n. Then we draw our normal distribution. Since it's within $90 of the mean, I want to draw a normal distribution where I'm shading between 2 lines. I want the mean tariff rate to be within $90. So that's mean minus 90 and the mean plus 90. And I'm going to use my formula for z, which equals the sample mean minus the population mean divided by the standard deviation divided by the sample size. So now I want to substitute what I know. My population mean minus 90 represents a sample mean, and my population mean plus 90 also represents a sample mean. So that's what we're going to use to substitute for x bar. So substituting, I have z equals the population mean minus 90 minus the population mean divided by 1,000 divided by the square root of 350. The means cancel, so I'm left with negative 90 divided by 1,000 divided by the square root of 350. Calculating, negative 90 divided by, parenthesis, 1,000 divided by second square root, 350. So I need to close the parenthesis for the root and for the denominator. Enter. Negative 1.68. And I get a z-score of negative 1.68. Because this is symmetric, the positive z-score should also be 1.68. So substituting, I have z equals the mean plus 90 minus the mean over 1,000 divided by the square root of 350. My population means cancel, which gives me 90 divided by 1,000 divided by the square root of 350. Calculating. Second, enter, retypes my equation. I'm going to arrow over, and I'm going to delete the negative for the 90. Use my delete, enter, and I do get a positive z-score of 1.68. And I get a z-score of 1.68. Again, the shortcut to find my positive z-score is to just change the sign of the first z-score, since my normal distribution is symmetric about the mean. Next, I need to find the area, going back to my calculator. Second, distribution, I want number 2, which is the normal CDF. I'm going to start with my lower limit, negative 1.68, comma, then my upper limit, positive 1.68. Since I'm using the standard normal curve, which has a mean of 0 and a standard deviation of 1, they're the defaults, I can just press enter. And I get an area of 0.9070427. So our area is 0.907. Continuing with our example, now we're ready to interpret the terms of the sampling error. The area between the z-scores, negative 1.68 and positive 1.68, is 0.907. The probability that the estimate for the population mean tariff rate of all railroad car shipments of ethanol within $90 of the true mean is 0.907. To recap the section, the sampling distribution of the sample mean. Sampling distribution of the sample mean for a normally distributed variable. Suppose that the variable x of a population is normally distributed with a mean mu and standard deviation sigma. Then for samples of size n, the variable x bar is also normally distributed and has a mean mu and standard deviation of sigma divided by the square root n. The central limit theorem says that for a relatively large sample size, the variable x bar is approximately normally distributed regardless of the distribution of the variable under consideration. So that the mean of the sample mean equals the population mean, and the standard deviation of the sample mean equals sigma divided by the square root of n. For the sampling distribution of the sample mean, if x is normally distributed, so is the sample mean, regardless of sample size, and if the sample size is large, the sample mean is approximately normally distributed regardless of the distribution of x.